Okay, it's again 16th of March 2023. This is session 2. It's 10:54 p.m. I'm at Mysore, Bhubaneswar. At SPS department, SPS building, and 107 CR. Okay. I just noticed that the classrooms are open whenever students want it. The computer center and the discussion hall are open till 2 a.m. and the SPS library is open until the last student leaves. So that's good. That's actually good. Someone did something there, and thankful to that guy. And this is second session of the day in order to understand the theory behind condensed matter. So essentially the source is lecture notes by David Tong of David Tong. Okay, so what I am reading is the second chapter called band structure. I've talked enough about it in the first part, and I essentially formulated the Hamiltonian in the last part, in the last session. The Hamiltonian, which was essentially E naught summation n minus t summation n plus 1 n plus 1 n. Yeah, so the important part of that session was identifying these parts. So yeah, the second, so the first session basically included the motivation behind things and what we're going to do and how we're going to explain things in condensed matter. And the first such was just letting a top model out and lattice, restricting the electron to only atoms which are essentially from a lattice, underlying lattice. We allowed the electrons to hop to its nearest neighbors, and so these assumptions led to construction of a Hamiltonian. The first assumption being that data which we're feeding is that the electrons are on lattice points, they cannot band up between them, and we label the states by n, Hamiltonian span of those n states, capital N states, n atom lattice. We constructed a Hamiltonian, a boring Hamiltonian, where there is no movement of electrons, but then we allowed a time evolution of psi, which told us that h psi should include other terms, cross terms in the sense that cross states. So so I kind of backstudied the Hamiltonian that Tong proposed in the lecture notes by applying it on an arbitrary state m, and saw that it mixes with m plus 1 state and m minus 1 state. That's what we mean by hopping, right? There's a probability to that. Tong claims that it's probability of t square by e naught square. I might prove it in some other time, but as of now I understand the Hamiltonian reasonably. I found the need of this cross n plus 1 n exterior products. They will essentially help us in getting h M to be mixed with things with its neighbors. So then we also declared that lattice is periodic, so that we label the n+1 state as the first state again, and there is no edge problems. So we essentially solved the tight binding model now, writing an arbitrary wave function as a linear combination of the n states, capital N states. So we write h psi is E psi, we expand it, and then we apply n, the bra n, then we get a linear equation, n linear equations I suppose, capital N linear equations, which Tong says are fairly common in physics, and they're solved by an ansatz like psi n is eikna. K is wave number. We kind of relate it to the lattice vibrations. Experiment we usually talked about the wave number stuff. So that is the recap of things. I don't want to go into the Brillouin zone now. I'll start from this linear equation right here. I'll start from this. So yeah. I'll redo the calculation, it's not a problem. So essentially what we need is H applied on some M is which essentially gives us this. V E psi. We substitute necessary things, which by writing psi as the linear combination. Okay. Which gives E naught psi m. Wait, what? Okay, I need to lower this fan down. You get wait, was this minus? It was plus. Minus. Oh, yeah, I'm doing red as minus. Okay. So I've lost some energy. I haven't had a good dinner. You see, that's the problem. Oh. Okay. Anyway, minus t times what you essentially get by looking at things is I guess this is what we get. Yep. Equals. Yeah. Now applying a bra n gives E naught psi n minus t psi n plus n plus psi n minus 1 equals to E psi n. So this is the linear equation. It's a linear equation and E and psi. It's a linear equation and whatever. Okay. Yeah, so this is a linear equation on psi n, and this is usually solved using an ansatz like psi n like I and a. Really? Well, the ansatz is this. Why is it even this? Why is that so? That's the homework. So this is the answers. The reasons in the background behind I gave it to homework. I don't have much energy to do mathematical methods right now. So you have this linear equation, set of linear equations. Let me read the tongue now. So these kind of equations arise fairly often in physics. Indeed, they will arise again in section 4 when we come to discuss the vibrations of a lattice. They solved by the ansatz psi n is eikni. Okay. Or if you want to ensure that the wave function is normalized, psi n equals eikni by root n. The exponent k is called the wave number. Okay. Quantity Phk plays a rule similar to momentum in a discrete model. Alright. Okay, alright. I'm taking the answers for granted. Okay. So now we'll talk about a few things. I mean, the answers simplified everything, right? But the crux of that was this, just this. You formulated a Hamiltonian. By feeding some data, some things, some reality. You've got a fairly good, nice looking Hamiltonian. You're trying to get this. What am I getting? Yeah, I know the eigen states. I want the eigen values of those states. I want the energy levels. Right. We are starting from the free particle. We know the free particle is E naught. I mean, it's basic momentum without interactions and stuff, without the hopping things. Yeah. So we relate the energy E with T, right? In some complicated sense, due to the dependence of different states on each other, different states, different neighboring sites on each other. So our motivation is to get E in terms of T. E in terms of T and E naught. What we want is E in terms of T and E naught. Right? Well, not E exactly, En. What? No, E. Yeah, any general state. Psi E. Okay. That's what we are looking for. So let's go ahead. Let's see how the ansatz cases when he gives out many things. So the wave number k has a number pop. Okay. Wave number property 1. Let's talk about k. So the first thing. First, the set of solutions remains same. If we shift from k to k plus 2 pi by a, psi n is same. This implies k belongs to minus pi by a to pi by a. What takes values in? Plus pi by a. This has a fancy name called a Blois zone. Just stumble there, Brillouin. It's Brillouin zone. We'll see why this is a useful concept that deserves its own name in section 2.2. There's also a condition on the allowed values of k coming from the requirement of periodicity. Periodicity of lattice says that psi of n plus 1 is simply psi 1, which implies that eikna is simply 1. Now this implies that k is quantized in terms of this. Right? This is a very important thing that Tong leaves out forever. He doesn't talk about it at all. The fact that k is quantized. Yeah, so I came up with few reasonings that large. So few remarks from my side would be that it's a large n, which implies it's a large n, which implies the discreteness is small. What do you mean by discreteness is small? Is implies that the delta k is 2 pi by ma is less than 2 pi by na is less than 1, right? I don't know how much this is true, but n is like the periodicity of lattice. It's not the number of atoms that it has, it's the number of atoms after which it repeats itself. Most of the time it's 2, 3, 4. It's a small number, and a is quite small, so delta k is actually quite big. So there is some subtlety here that David Tong chooses to ignore it completely. But yeah, one thing I know is if large n, say, let's do mathematics here. If there is large n, the delta k will be small. Delta k will be small. Discreteness can be ignored. Discreteness in k can be ignored with respect to its domain, basically Brillouin zone, right? The fact that it has this Brillouin zone structure, and it starts from it starts from here, is that, but it only takes like this. This is the picture that you need to look at it, right? It's not continuous. Expected picture to be kept in mind. After which it repeats, lattice repeats. unit cell, basically a unit cell to fill lattice. It's quite small, right? It's like two, or 2, 3 something. Quite small, and this puts us in a fix. Why do we ignore? I mean, this can be a big number. A small number, big pi by a. It's it's 2 times pi by a, and you divide by half, and you just get 2 or 3. I mean, if n is 2, it's basically pi by a, right? It sucks. That sense it sucks, right? So yeah, anyhow, we'll proceed further, assuming physically it's quite reasonable. Okay, let's take FCC, right? Face centered, just 2. Capital N is 2. So large than approximation, that's just bullshit. So it's 2 times pi by a. It's 2 by n times pi by a. The quantization of k. Right? Exactly. So oh, what? No. What? Yeah. So it's also true that yep. Oh no. No. Yeah, actually, this kind of is bad, because as we'll see, this n is something different. It's not just a, it's not just 2. Okay, it's not just 2, but it's something more. It's these repetitions of unit cells, but the lattice potential takes some space before repeating itself. That's what my theory is. So that in that way, In that sense, n is large. N is actually large. Let's say large enough, right? Such that it is 2 by n is less than 1, right? N is greater than 2. Maybe it is greater than 2. 10 atoms, 20 atoms, 100 atoms. I guess physical it's this big. Yeah, but you're not just theorizing something, some bullshit and letting it go. We'll look at it, we'll revisit this problem, revisit this when required, right? So in that sense, this has to be bookmarked. It's a question. This also has a question. Yep. Do I have another homework? Yep, I have another homework. The fact that the probability is t square by naught square. Okay. 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 Yeah. I mean, to speak about remarks explicitly. Till now there was no problem. I just cooked up some things and stuff. Okay. Explicitly, the above these gaps. I mean, these gaps basically are n in number, not precisely gaps. Basically states. Right, 2 pi by na times n is equals to pi by a minus pi by a, which is 2 pi by a, is equals to 2 pi by a, n states in a Brillouin zone. That's what the realization is. Alright, but that's what we expect, as it's the dimension of a Hilbert space. The states 2.3 form a different basis. Okay. Wait. Okay, I started out with some states. We expect n states and quantum states. That's what we expect. And the second inference is that we've got something called this. This implied k has n values n can take n values in a BZ in a Brillouin zone. That means psi n has n take n values. within the Brillouin zone, there are exactly n quantum states of the form 2.3, but that's what we expect as it's the dimension of the Hilbert space. Wait, how do we know that exactly implies psi has n values? Psi can take n values, implies in a busy n states, n quantum states. N states, so that's what this proof tells us. States, and that's what we have. So we deal with the Brillouin zone. So the allowed values of k are the Brillouin zone values. Whatever the shit the sunsat's pulled off, it says that k is quantized. It is also restricted to the Brillouin zone to let things stay cool. That's what it is. So you got a good consistency between n states and your answers. It's okay. States of the form 2.3 have the property that psi n plus minus 1 equals your I plus I k times psi n. That's true. This immediately ensures that 2.2 is solved for any k with the energy eigenvalue. Okay. Now, what this means is E naught psi n minus t I k a minus e power minus I k a psi n is equals to E psi n, which gives, okay, why did I put it? It's plus, which gives E is equals to E minus 2t cos k. We got something here. And we got what we expected. E of t comma E naught. So what next? The spectrum. So you get an energy of an arbitrary wave function. Energy of an arbitrary wave function within that Hilbert space, of course. Within the Hilbert space. Within the Hilbert space under steady. Within the Hilbert space under steady. I mean, it's not like every function in this world. You can write every function of that Hilbert space. You are still in a space. Within the Hilbert space under what? Under consideration. Basically the Hamiltonian dictates everything. That's what dictated. So Okay, so that's the energy of an arbitrary wave function within the Hilbert space. So yeah, I don't want to write the statement, but I'll just keep it. So I'm gonna rewrite this 2t cos A. Okay, so the states are labeled by k, right? So-called momentum that we eventually assign it to, but now labeled by k, and they also form a basis. I can just see him not doing anything. Anyway, states are now labeled by k, t cos k. If the picture of the energy looks something like this. Okay, in some sense. What the hell? So yeah, that's the EK 0 K. This is plotted for A equals to T equals to 1, E naught is 2. Okay, that's how it looks like. The spectrum shown for T is 0, T greater than 0, the plot was made with okay. The states with K is 0 describe the electron which moves to the right. Those with K less than 0 describe the electrons moving to the left. There's a wealth of physics hiding in the simple result, and much of following sections will be fleshing out these ideas. Okay. The electrons do not exist. Okay, some pertinent points of physics hiding in the above. So one of them is arbitrarily small interactions, that is interactions with the nearest neighboring sites. Interactions result in a completely exaggeration करते हैं shit. Delocalized energy eigenstates. I mean, once you mention it, there is no going back, you know. You mentioned it, that's it. You use it again by only giving some reasoning. I mean, like, you assume a lot. When you state it first time, you imagine like, people are fine with it, right? And then you start from there. That's fucking god, there are 4 dusters. 5 dusters. Shit. Holy fuck. Okay, second point is the energy eigenstates H naught were completely degenerate. Adding the hopping term lifts this degeneracy. Instead, the eigenstates are labeled by wave vector k and have energies that lie in range. This range of energies to band, and the difference between maximum and minimum energy is called the bandwidth. In a simple form, we have just an energy band. In subsequent moments, you'll see multiple bands emerging. What was the second point again? It was completely degenerate, but adding the hopping term left this degeneracy. Instead, the eigenstates are labeled by wave vectors k and have the energies that lie in range. Okay. So degeneracy is lifted. Degeneracy is lifted. P square by 2m states, right? Before it was p square by 2m states. Now minus k and plus k have different energy states. Yeah, but if you just see that, you still have some sort of degeneracy, right? Right, it is plotted from minus pi to pi. Minus pi. It's the first below zone. It's plotted in the below zone itself. The degeneracy is lifted. The degeneracy is lifted by hopping parameter. labeled by K, have energies that lie in E0 minus 2t to E0 plus 2t. This range of energy is referred to as to a band, and the difference between the maximum energy is called bandwidth. Bandwidth equals to 40. Okay. Other thing, for k smaller than pi by a, you can Taylor expand 2.5 as E0 minus 2t plus t s square k square. Okay. Taylor expanding to a constant. This takes the form as a free particle. Free particle energy up to a constant. This is telling that low energy, low momentum particles are unaware that they are moving on a undirected mass. And this is the act of the moving on conditions effective mass unimpeded. Effective no direct. There's Q responsible between the properties momentum and position. First question from that is the space is made finite. For example, a particle moving in a circle, the momentum becomes discrete. We also saw this as above as periodic boundary conditions before the wave. Reciprocity between the sense that periodic x bar implied k discrete implied k discrete like in periodic boundary conditions, like in momentum particle in a box, or particle moving in a circle, etc. However, our tight bonding model also exhibits the converse phenomenon. When we make space discrete, Momentum becomes periodic. Periodic. That's what the tight binding says, right? Tight binding. Right? It has to lie in Brillouin zone. Brillouin zone. Brillouin zone. Brillouin zone. Discreteness. Really? In some capacity, we introduce methods, non-mathematical methods, of course. And some non-rigorous capacity, we introduce discreteness is the Fourier transform of compactness. Yeah, we look at metals and insulators, realizing them with this 1D model. Nearly free electrons in 1D model. Nearly free electrons is an important thing. You get the most of it. Most of what the hell am I talking? You get so much out of it. There's a lot of degenerate perturbation. There's a lot of perturbation theory. There's a lot of physics to flesh out from it. There's a lot of mathematics to set things right. Yeah, it gives you bands, man. It gives you bands. It's not easy. It takes some effort to do it. I can do it. I'll start this stuff from tomorrow, but flockometrics, okay? Okay. One dimension is a long thing. You have to slowly understand it. Just like these. So I haven't done much in the last hour, I see. Apart from solving the tight binding model in 1D. Okay, that's cool. And next stuff is to apply them, right? To apply them into metals and insulators, to just realize few things. Then you look at nearly free electrons. You apply the perturbation theory, and you apply your degenerate perturbation theory and such stuff. You get to somewhere. And yep, there are very interesting results that follow. And then you try to compare nearly free electrons on tight binding model. What happens? Okay, that should be interesting. Okay. 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 I have also assignment 5 on probably compactness due. I should do that. Assignment 5 of metric spaces. That's interesting thing. I was waiting for it. I didn't see any I didn't see any explicit compactness stuff, but I guess they're related. But anyway, I don't have much energy left to delve into much today. So I can go to canteen, have some food, and then come back and study these things. But the problem with this is, will I be able to do there's a lot of stuff, right? I wish I could do everything today. The whole 1D, well, the whole second chapter is I need to sit all night. That I'm not going to do. My plan is to just throughout the weekend complete this whole theory and assignment 5. That's more than what I can even think of. That's just good. So anyway,